Hello there. In this video we're going to review the concepts associated to a Poisson distribution and introduce new concepts associated to the exponential distribution, and also show that there is a connection between these two distributions if you look at it from the right perspective. So as we already know, the probability mass function for a Poisson random variable x is given by e to the minus lambda times lambda to the x over x factorial, and the probability density function for an exponential distribution for random variable t is equal to 1 over beta times e to the minus 1 over beta times t. Here beta is greater than 0, and ideally lambda is greater than 0. So let's begin by taking a look at the Poisson distribution, what its random variable represents, and how problems can slightly be manipulated that you may be presented with in real life. So the random variable x represents the number of events that occur in a fixed interval of time, with the expected number of occurrences in that interval, which we sometimes abbreviate as mu x, to be equal to lambda. So lambda is a parameter. So here's a question that may arise. Suppose that an average of 5 car accidents occur between the hours of 12 p.m. and 12 a.m. in some given city. So what are some possible variations of this problem that people could ask? So here's a question. So what about from 12 p.m. To say 12 p.m. the next day? Namely, what is the average number of accidents that occur in this interval of time? Now, one can say, oh, well, the interval is multiplied by 2 in terms of length, therefore we can just multiply 5 by 2, and the average number of occurrences would be 10. That is not necessarily right. So it's not necessarily equal to 2 times 5, which is 10. Now, why is that the case? Well, it's possible that more accidents occur in the evening rather than the morning, right? So this is only true in general if the intervals are identically distributed. Right? So if they're identically distributed, then this would be the case, right? But sometimes they aren't. In practice, they usually are not, right? But nonetheless, the number of car accidents, so we're going to let x be the number of car accidents between 12 p.m. and 12 a.m. And we're going to let 2x represent the number of car accidents between 12 p.m. and 12 p.m. the next day. Right, so clearly both are random variables, and if the car accidents are independent of one another, then both of them are Poisson. Right, so what is going to be the probability mass function for the variable 2x? So the probability mass function for 2x is going to be equal to what? So first we need to figure out, okay, what is the average of that? So the average of the random variable 2x is going to be equal to 2 times the expected value of x, and we know the expected value of x is going to be equal to lambda. So this is going to be our lambda for the p2x distribution. So it's going to be e to the minus 2 lambda times our new lambda to the power of x all over x factorial. Right? So for the general case, so moreover, for some t in the set of positive reals, the expected value of x times t is going to be equal to t times ex, which is going to be equal to t lambda, which means the probability mass function for the random variable xt is going to be equal to e to the minus lambda t times lambda t to the power of x all over x factorial, right? So a question is, well, can we really use this as an estimate, right? All right, so let t be the interval length in general. So t is equal to 1 corresponds to the original length of the interval, right? So lambda hat, which is going to be an approximation for lambda, is an approximation for lambda, which is the expected value of x. So we're trying to figure out a good estimate for x times t. So is multiplying lambda by t really an unbiased estimator for the true average over that course of that interval, right? So let's see if we can generate a proof for that. So what is the expected value of the number of car accidents, or whatever, in this new stretched out or shrinked interval of time? So in general, this is going to be equal to the expected value of the number of occurrences divided by the length of the interval. Now, why is that the case? So remember, average is pretty much equal to occurrences divided by length of time, right? This is pretty much similar to the physics expression. Velocity is equal to change of distance, so delta x over delta t, for example. So number of occurrences, or the change in occurrences over the change in time. So it's pretty much almost the same exact concept. So if this is going to be the case, then properties of expected value say this is going to be equal to 1 over t times the expected value of x. Now, there is a difference between expected value of lambda and expected value of x. So the expected value of lambda is the expected average in that interval. The expected value of x is the expected number of occurrences in that new interval. So we know the expected number of occurrences in that interval is going to be equal to lambda times, so the average of the original times this multiplicative number t that we're stretching by. And as we see, the 1 over t's will cancel, and we're just going to be left with lambda, which is going to be equal to the expected value of x, right? So that's nice. So that means lambda hat is an unbiased estimator for lambda, right? That's the conclusion. Therefore, lambda hat is an unbiased estimator for lambda, where lambda hat is the observed number of occurrences in our interval of time. Right. So that's a good conclusion. Now, since we're using lambda hat as an approximation for the number parameter lambda, there's going to be some error associated to that. So being able to calculate the standard error is a very useful tool in order to know how we can sort of control or bound that error. So what we're going to do is we're going to find the variance of this parameter lambda hat. So that's going to be equal to the variance of x divided by t. So by properties of variance, we can quadratically factor out this 1 over t to become 1 over t squared times the variance of that random variable x. So x is going to be the number of occurrences in that stretched out interval, and the variance is going to be equal to the expected value of that random variable by properties of Poisson. So it's going to be equal to 1 over t squared times the expected value, which we already know is going to be equal to lambda t. Therefore, we can cancel out one of these t's, and we're just going to be left with lambda divided by t. Since lambda is positive and t should be positive as well, then we have the standard deviation of this parameter estimate to be equal to the square root of lambda t. Now typically we will abbreviate this instead as sigma lambda hat to be equal to lambda over t, and this is our standard error. Standard error. So now what we're going to do is we're going to turn to the exponential distribution and explore that a little bit. So again, note that t is going to be a positive real number, and we're going to let t be an exponential random variable with parameter 1 over beta, and we're going to define this to be equal to lambda. And you're going to see algebraically why this is going to make sense in a moment. So therefore, the probability density function for t with parameter little t is going to be equal to lambda times e to the minus lambda t, and this is true for t is greater than or equal to 0. So by properties of probability, what is the probability that capital T is bigger than little t, this number t, for some t? So by definition, that's going to be equal to the integral from t to infinity of lambda e to the minus lambda x dx, where x is a dummy variable here. So we know that's going to be equal to, by the fundamental theorem of calculus, minus e to the minus lambda x, evaluated as x goes to infinity and as x goes to t. So this is of course going to be equal to e to the minus lambda t, and then we're going to multiply this by 1. So another form of 1 that we can replace this with, if we're clever, is we can replace it with lambda t to the power of 0 divided by 0 factorial, right? So what exactly is this? Does this look familiar? So this is the evaluation of the probability mass function for a random variable xt evaluated at 0. So this is one connection between the exponential. Remember, x represents the random variable of the number of occurrences in some interval of time, and the exponential distribution measures the probability that the next instant of an event occurs larger than some time t. So suppose you have 5 occurrences in an interval of time, and you want to know how long it takes until the next event occurs, right? So Poisson, exponential. They're talking about the same scenario or the same process, sometimes referred as a Poisson process, but they're answering different questions. Now, side note for this, and this is primarily targeted to the exponential distribution, but it's also tied to the Poisson distribution as well. So we're going to let t be exponential with parameter lambda, and we're going to let t1 and t2 both be positive real numbers. So I'm going to go back to conditional probability for the moment. So what is the probability that the random variable t is larger than t1 plus t2, provided that t is already greater than t2? So if 5 accidents have occurred within the hour, what is the probability that more accidents occur in the next interval of time, for example? Of course, that's in perspective of x, not necessarily t. So let's actually see what this works out to. So I'm going to tell you the result. This should just equal to the probability that t is greater than t1, right? So even though it's already past t2, it actually has no effect on the next event, right? So this is what we call the memoryless property of exponential random variable t, which can be viewed in another way as past doesn't affect future, which is extremely useful. So let's see if we can give a proof and justification for this. So the probability that t is greater than t1 plus t2, given that t is already larger than t2, by definition of conditional probabilities, that's going to be the probability of the event that t is greater than t1 plus t2 and the event t is greater than t2. So the probability of, remember the probability of A given B is the probability of A and B all over the probability of B. Alright, so what can you say about these two events? Well, they share some overlap, right? So t is greater than t1 plus t2, so let's draw out a little graph. So t1, t2, and then infinity. So t is greater than t1 plus t2. So t1 plus t2 is, say, out here. t1 plus t2. Assuming that they're both positive. Could be in between, we don't know. Let's assume it goes above. So t1 plus t2 is going to be the first interval. So it's going to be all the way out here. Actually, no. The probability that t is greater than t1 plus t2 is going to be over here somewhere. And the probability that t is greater than t2 is going to be somewhere over here. So clearly those two events do share some overlap, namely this t1 plus t2 part. So they are not mutually exclusive. So this is going to be equal to the probability that t is going to be greater than t1 plus t2, all divided by the probability that t is greater than t2. So now let's look at the density function representations for these. So these are both exponential. So the top is going to be equal to the integral from t1 plus t2 to infinity of lambda e to the minus lambda x dx. And the denominator is going to be the integral from t2 to infinity of lambda e to the minus lambda x dx. So clearly these lambdas cancel top and bottom, no big deal. And once we evaluate this, you're going to have that this is going to be equal to minus e to the minus lambda x. Evaluated as x goes to infinity, as x goes to t1 plus t2, all divided by minus e to the minus lambda x, as x goes to infinity, as x goes to t2. So once we substitute everything in, you're going to have 0 minus some things. Once you simplify, you're going to have e to the minus lambda t1 plus t2 all over e to the minus lambda t2. So they're the same bases, therefore we can subtract exponents. So e to the minus lambda t1 minus lambda t2. Minus minus is going to be a plus lambda t2. Lambda t2 is going to cancel, no big deal. So this is just going to be equal to e to the minus lambda t1, which of course can be shown to be equal to the integral from t1 to infinity of lambda e to the minus lambda x dx, which is just the probability that t is greater than t1. So let's see an example of how this theorem can be used. So, example. So suppose we are in a car waiting at a stoplight, and we have already waited 15 seconds. What is the probability that we have to wait a total time of 40 seconds or more? So we can think about this, and let's assume that the waiting time is exponentially distributed with some average lambda, right? So we've already waited 15 seconds, so this is a condition, right, for some probability. So what is the probability that we have to wait a total time of 40 seconds or more? So the probability that t is greater than 40, assuming that t is greater than 15 already. So we can look at this from this memoryless perspective. So if we were to shift everything down and, pretty much subtract 15 from this, this is the same thing as the probability that t is greater than 25 plus 15, assuming that t is greater than 15. Because the only thing that we do not know is what happens in these next 25 seconds. So this is pretty much like the equivalent of saying the probability of waiting an additional 25 seconds, right? Which is the same thing as the probability that once we get to the stoplight that we have to work or wait more than 25 seconds to start. assuming that nothing else has happened, right? So if this problem is confusing, you can use the memoryless property of the exponential distribution to solve this problem instead, right? And that's just a special property associated with exponential RVs. Anyway, that's just some discussion on Poisson and exponential, a couple properties, a couple things on how these things are connected. Definitely a lot more things can be said about Poisson processes, but we will wait until a later time to go into more detail. Hope you enjoyed.